Hello, everyone. Welcome back to your sessions of probability. What I want to do today is to go over the confidence interval and the hypothesis testing of two variance, two population variances. So I have two populations, and I want to see whether the variance of each can be assumed equal or not. So remember, we touched on that when we were talking about um, the confidence interval of two population means. Can we assume their variance is equal or not? And we said we usually prefer to use the assumption that the variances are not equal. But in other cases, we want to know if the variances can be assumed equal because we don't want, remember I told you earlier that because the variance is a measure of error, we want if we have two samples, we want to see which one has less error or better production, better uniformity. Okay, so that's in that case we use the this test, and this test is called the F test. And you will see that we use the same test, say in uh, analysis of variance, and sometimes and even in regression. So it's a powerful test in these areas more than in the case of population parameters and so on and so forth. So it's called the F test. So it's for students who failed. Oh no, I'm sorry, just kidding. No, that's not the F test. Okay, so what is the F test? The F test is basically a ratio or two ratios divided by each other. The top one is S1 square over sigma 1 square, and the bottom is S2 square over sigma 2 square. In fact, it's a ratio, so to speak, of two chi-square variables, but that's a discussion for another day. So if that's the case, we can we can find a ratio of sigma 1 square over sigma 2 square, right? Meaning, same thing like we did. Remember when you had, for example, z equals x bar minus mu over sigma over root n, and we wanted to separate mu. Here I want to separate sigma 1 square over sigma 2 square. However, in in the tests or in constructing confidence interval, I want to see always whether two variances are equal or not. So the null hypothesis invariably, in the case of confidence interval, I'm not talking about regression or ANOVA, but here we want to check to see if these are equal. So our null hypothesis is that sigma 1 square equals sigma 2 square, meaning if I divide them, they cancel each other. But let's see how it works. So first of all, the F distribution, like the chi-square distribution, cannot be negative, right? It's a ratio of two positive values, so it's impossible to be negative. And that's why it starts from here, very similar to the chi-square, okay? But that distribution, in order to draw, remember the chi-square depended like the t on the degrees of freedom. And you would say, wait a second, here I have 2 degrees of freedom. So if I took m units from population 1 and n from population 2, then I have the numerator degrees of freedom would be m minus 1, and that of the denominators would be n minus 1. So which one do I use? No, you use both. So this would be the F distribution for m minus, so for example, alpha and m minus 1 and n minus 1. So it has 2 degrees of freedom, numerator and denominator. So this value, for example, remember the way we mentioned alpha over 2, we go from the right, but when we do the cumulative, we go from the left. So that's a little tricky. Like this one would be called f alpha over 2 numerator degrees of freedom that I'm going to call nu1 and nu2. And this is f of 1 minus alpha over 2, nu1, nu2. Now, we are using calculators or computers, so we don't have a problem finding the f values. But in the old days, when we just constructed tables, we found a very interesting relationship. So they will show you, for example, f for 0.01, 0.05, 0.1, but not for 0.9, 0.95, and 0.99. Why? Because it turns out that if you want f of, say, 0.975, 1 minus alpha over 2, nu1 and nu2, that is exactly 1 divided by f of alpha over 2. No, not nu1, nu2, nu2, nu1. So now I don't need to show you, the cumulative, I'm sorry, the F value at zero point 0.9 or 0.95. If I know 1, 5, and 10, I can find 90, 95, and 99 by just taking the reciprocal, but I make sure I reverse the degrees of freedom. So now I can say the probability, I want the probability that S1 square. In fact, if you divide, you can multiply by that, right? If you divide by a fraction, you multiply by its reciprocal, should be greater than this guy, which is f of 1 minus alpha over 2 nu1 nu2 less than f alpha over 2 nu1 nu2. Right? And we said, so if I want to do the reciprocal, right? So anyway, let's put it sigma 2 square, it doesn't matter, over sigma 1 square would be greater than, I'm going to multiply by sigma s2 square over s1 square. So I guess I get s2 square over s1 square times f1 minus alpha nu1 nu2 is less than s2 square over s1 square f alpha over 2 nu1 nu2. Okay? Now I can take the reciprocal to make it, usually we do sigma 1 square over sigma 2 square, right? So if I take the reciprocal, the less than becomes greater than, and I take the reciprocal of that, which is s1 square over s2 square divided by, so 1 over f of alpha over 2 nu1 nu2, and it's less than s1 square over s2 square. 1 over that, but 1 over that, remember, is f, I'm sorry, I said over 2 here, right? It's the reciprocal, 1 over that is f of alpha over 2 nu 2 and nu 1. So I switched using this equation. And that would be the confidence interval, or 1 minus alpha, 100 times 1 minus alpha percent confidence interval of sigma 1 square over sigma 2 square. If I'm testing, I usually say, okay, the null hypothesis is that sigma 1 square equals sigma 2 square, right? I can write it. I usually prefer to write all the parameters on the left and the constants on the right. So I would say f sigma 1 square over sigma 2 square equals 1. And then the alternative can be sigma 1 square over sigma 2 square is doesn't equal 1 or less than 1 or greater than 1. So depending on the case, let's say doesn't equal 1 or greater than 1 or less than 1. Alpha is 5%. I would reject. Notice my f now, if sigma 1 equals sigma 2, meaning sigma 1 square over sigma 2 square equals 1. My f would be s1 square over s2 square. I just divide the variance of the sample variances. Okay? That would be the f calculated. And once I get the f calculated, I check to see is it between these two guys or not. So it's really pretty straightforward, as we can see. It's just if you have the table, I think I don't have an example, but or maybe I can find one. Um, let's pick one from a book and see how we do that. Hypothesis testing, two samples. I think it's, yeah. Okay. Okay, so here, for example, it says in a series of experiments to determine the absorption of certain pesticides on skin, measured blah, 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 in micrograms. For pesticide A, so for A, pesticide A, we took 6 specimens, so N1, or if you call it N1 or M equals 6, the variance was 2.3. And for pesticide B, the variance of 10 specimens was 0.6. You can see there is a difference, right? But can we conclude that the variance in the amount absorbed is greater for A than it is for B? That's all. You see, that's all what we have. So, very simple. First of all, I would say the null hypothesis is that sigma 1 square over sigma 2 square equals 1, which is sigma 1 square equals sigma 2 square. That would usually be the case. I will never tell you, oh, can you test to see if the variance of population 1 is 5 units square more than, doesn't make any sense. I want to see whether I can consider them equal or not, right? I will never say, oh, it's greater than a specific, or is it twice the variance of the second? Why do I care? Right? I will never use that ratio in anything. So here, the alternative hypothesis is that sigma 1 square over sigma 2 square is greater than 1. And I want to check that at alpha equals 0.05. So the way we do it, we can go here and look at stats, go to the tests, and you would see, hopefully, I have it here. I never checked. I should have checked, right? Chi-square, two sample F-test. So I select two sample F-tests. No, I don't have data. I have stats. So it asks you, notice it doesn't ask for the mean. I don't care about the mean, right? I want to see just the variability in the samples. So S1, Sx1, in fact, I have S square. They want S. So I would say the square root of 2.3. Then N1 is 6. S2 is the square root of 0.6. And N2 is 10. What is the alternative? The alternative is that sigma 1 is greater than sigma 2. Notice that this is done for sigma, which is the square root. Well, if sigma 1 squared is greater than sigma 2 squared, then sigma 1 will also be greater than sigma 2. So some people do it for sigma here, but basically it's an F-test. We are considering the variances. But as I said, if the variance of one is greater than the other, then the standard deviation of the first is greater than the other. Okay, that's what I want. And here is the calculation. So I get F equals 3.833. And the p-value is 0.038, which is less than 0.05. So I'm going to reject H sub 0 and conclude that sigma 1 square is greater than sigma 2 square. at zero point zero 0.05 level of significance. Okay, you always have to say at what level are you like basing your conclusion, because if you tell me I want zero point zero 0.01, I want to be really confident, then I wouldn't reject because 0.038 is greater than 0.01. So you have to always tell me what level of significance you are running the experiment at. I'm going to keep this for next time, because not next time, well, one of the sessions, the next sessions in this series, where we will see how we can calculate that using our studio, which is basically also is single line f, like f dot test, right? Or var dot test to be more accurate. So it will do it for the variances, but again, you can take the square root, and then it will also show you a confidence interval for that. Notice that if I do a confidence interval, the lower limit would be higher than 1, and the upper limit, of course, would be infinity. So the 1 will not be included. Since I rejected it here, then the confidence interval. So for example, can we, uh, oh, these are the tests. So distributions. Oh, in fact, I wanted to show you something. If for the one we did, we can draw it also, and you can see that the distribution is skewed. You see, it's very highly skewed here, and it gives you both. So you can see that the F value and the P value, which was less than 5%. Of course, you can always draw that if you wish. Okay, so I think that's it for today. I just wanted to go over the F test and tell you, give you this relationship, which nowadays is irrelevant unless you are solving the problem without a calculator and with tables, which I doubt you would be asked to do. I mean, this was thing of the past now. But I want to show you where do they have the tables? It should be near the end. Before the index, no, or maybe before the solutions. These are the answers to, oh my God. Oh, here they are. And you can see here, when we go to the F distribution, let's start from the beginning. They start here. And you can see they give you alpha of 0.1, 0.05, 0.01, and 0.001. They don't give you 0.999 and 0.99 and 0.95 and so on. No, they give you those. So if you want the 0.95, you would say, okay, I'm going to switch the new one and new two, the degrees of freedom, and read the value. And that would be one over that would be what you are looking for. So you can see for all of those, they give you degrees of freedom of 1 up to 60 here. Of course, they jump, and then uh, they increase. So this was for new 2 from 1 to 9, and then they repeat the whole thing for 10, and it's a long way. And then from 21 to 31, and then from 32 to 120, a lot of curves. A lot of curves. We don't need those at all now, of course, if you are using a calculator or a computer. Okay, so that's it for today, and I wish it wasn't that bad. I mean, it's pretty straightforward. You are just dividing S1 square over S2 square and see whether they fall within the limits. Okay, as I mentioned next time we'll see how we do that with our studio, and probably would be also a short session. Thanks for your time. Hope to see you soon. Have a nice day.